Sticking with unions, but now something quite different. We will see through a lens darkly with Mike Hudson.
It's great to be here and to give you an update on the weak lensing. I'm primarily going to talk about weak lensing side of unions. Weak lensing is hard work, as I'll try to explain later if time permits. So there's a big team separated into blue for France and red for Canada and a sort of orangey color for a couple of Germans. Why do we care about lensing? I'll give you the standard motivation, which I think is actually an extremely powerful motivation, even though I've said it a million times. Dark matter, of course, you know, is most of the matter in the universe, and it's really the dark matter evolution which drives the structure of everything from the scale of galaxies and larger. The dark energy, we think, is more or less uniform, so it doesn't play a role in the formation of structure. So if we want to understand galaxy formation, if we want to understand cosmology, we have to be able to somehow see the dark matter. But of course, as you know, and you've learned in your courses, dark matter doesn't absorb, it doesn't scatter, it doesn't interact, etc. So the only way really to visualize dark matter and to measure it, of course, is through the technique of lensing. And so this brief little cartoon illustrates that, you know, the path of light is bent as it comes from a distant galaxy. And not only is it bent, but a circular bundle of rays is distorted into an ellipse. And it's that distortion and the fact that we know that galaxies don't have a preferred orientation on the sky that allows us to extract the dark matter information from the observable, which is the shapes of the galaxies. And that has to be measured extremely precisely, and it's hard work, to be blunt. So I'm going to talk about a few science topics. The goal here is just to give you a flavor of some of the things that we're doing. The hardest thing to do is the thing at the bottom, cosmic shear. So that's the stuff where we don't have results yet, but we're expecting them very soon this summer. From a technical perspective, the other topics are a little bit less technically challenging, technically less demanding. So I'll spend a few minutes talking about each of those just to give you a sense of the kind of things we can do. There's lots of other stuff you can do with lensing. I'm not going to talk about strong lensing at all. I'm only going to talk about weak lensing. But there is a talk by Storfer later. There's other weak lensing topics like measuring cluster masses, the kind of clusters that the previous speaker spoke about. And there's a remote poster on that by Taylor. Here's a nice result that's never been done before. We measure, at least not with lensing, we've measured, it's well known that, for example, in a galaxy, the stellar mass of the galaxy is correlated with the halo mass in which it lives. But what we've done here is actually correlated, instead of the stellar mass, the mass of the black hole in the center of that galaxy. And that's enabled because we can estimate the black hole halo mass from spectroscopy, slow spectroscopy. And it's one of the big advantages of unions that it has overlap with these spectroscopic surveys. So we can do a lot of science projects that correlate the weak lensing with spectroscopy, which other competing surveys such as DES struggle to do because they don't have large amounts of spectroscopy in the south. So here we see indeed a correlation between more massive black holes live in more massive halos. Seems to agree roughly with several simulations, which are shown on the right. There is another way of estimating this through the clustering of these objects, and that relation is shown in the light brown, and it seems to disagree. We don't understand it. We believe ours is more direct measurement. The clustering is indirect. You do it through the clustering and a bias, a model of populating dark matter halos. So this is the kind of stuff you can start to do. As I said, we've known for a while that the stellar mass in a galaxy is correlated with the halo mass, but maybe that's not the whole story. Maybe there are other galaxy properties that correlate with the halo mass as well. And in turn, turning it around, will say that there are other, it's not just a simple matter of figuring out what the efficiency of galaxy formation is. There could be other parameters that drive galaxy formation. And so in this plot, we're looking at red galaxies in different stellar mass bins shown in the four panels. The vertical axis is the simple quantity you measure in galaxy-galaxy lensing is proportional to, you can think about it as a surface mass density. So higher is higher density and hence higher mass as a function of projected radius in 4 different mass bins. And what we've done here is split those up into large galaxies and small galaxies of the same stellar mass. And we find indeed that the curves, in some cases, almost sit on top of each other, top right. But in other cases, it's not. In other stellar mass bins, that's not the case. It tells us there's something more complicated going on in galaxy formation, which probably isn't even included in most models of galaxy formation. We're still trying to interpret what this means from a physics point of view. We see the tidal stripping of dark matter halos. You heard all about streams. So stellar streams of dwarf galaxies as they're destroyed. But of course, what happens first is the dark matter halo around those is also stripped out and destroyed, and it shrinks the mass of the galaxy. Happens first because the dark matter is further out. Okay, so what's plotted here is for objects of satellite galaxies in a cluster of about the same stellar mass is the ratio of that halo, or you might call it a subhalo, because that's living in a larger halo, the cluster itself. That's why it says M sub. The ratio of that halo mass, that satellite halo mass, to the stellar mass, as a function of now the distance that the satellite is away in projection from the center of the cluster. Okay, and what you see, which is perhaps not a big surprise, but it's nice to see it confirmed observationally, is the simplest interpretation of this is that the further out you are, the less you've been stripped and the more of the mass you retained around that satellite galaxy. The ones that are in the center, down on the bottom left, have been in the cluster a long time, and they've orbited through the cluster many times. They've been tidally stripped and so have less mass left over. Okay, and so this will help us understand how these processes behave. We heard earlier in the previous talks about unions, about mergers. Sarah Ellison's group has produced a nice machine learning way of detecting post-merger galaxies that was talked about. We have now tried to say, well, do these mergers, what is the dark matter structure around the mergers? And we can do that. So on the left-hand panel are the post-mergers. On the right-hand panel is our a set of control galaxies of the same stellar mass, same color, they're mostly red. And on the vertical axis is a quantity called halo concentration, which essentially, if you're not a galaxy formation person or cosmologist, tells you how compact the dark matter halo is. Okay, so there's an interesting and intriguing hint that the post-mergers have a very low concentration, much lower than you would predict in a standard NFW model, Navarro, Frank, and White, which is a classic model for the dark matter distribution. Okay, these are all slightly different scales, so it's good to put them together. So unfortunately, it's just like at the 2 sigma level, the difference between these two. And so formally, there's no significant difference, but the hint is that the concentrations are very different. So with larger samples, we hope to tighten this up and see if there really is a difference in the merger structure of these post-merger products, which you might not be surprised by because the dark matter halos are combining together. The NFW model assumes that they're sort of in equilibrium, which they clearly aren't if they're just merging. A few more topics. So zooming out to larger structures, with weak lensing, we can also probe structures on scales larger than galaxies. So one of those things are filaments in the cosmic web. Okay, so the left-hand picture is an in-body simulation showing that halos form in filaments. And by stacking many such pairs, we can measure these. It's not the greatest. Colors look better here, as people always say. But we can start to stack those pairs together, and we see a sign of the filament between them. So there's excess mass. This is a projected surface mass density, you can think about it, but it's dark matter, right? Not light. And there's a hint of an excess material between the two knots, which are the 2 halos that live in that filament. Likewise, cosmic voids are big underdense regions, bubbles, if you like. They're enormous size, 60 or larger megaparsecs. And with UNIONS lensing, we've made the best detection of this void signal that's ever been made. This is going to be submitted soon, hopefully. The top panel shows that excess surface mass density, but now it's negative because it's a void. It's lower than average. And if you do an Abel inversion to figure out what it looks like in 3D, you can try to extract the three-dimensional profile of the void. And so we see a negative underdensity, a hole, if you like, as a function of radius on the x-axis. Intriguingly, it's not as... if it was completely empty in dark matter, that quantity delta M would be -1. That's the way it's defined. So that voids are not empty in dark matter. We are seeing dark matter in the voids, just not as much as in the average universe. And in fact, there's a slight hint that they may be less underdense than the models predict. Again, the usual answer, we need better data. Okay, probably have about a minute left. There are several tensions going on in cosmology right now. Hubble tension. Desi people talked about dark energy evolution in a non-lambda way. There's a third tension, which is called the S8 tension, but you can think of that as how smooth the universe is. And we can measure that with a quantity called cosmic shear, which correlates the shape of a galaxy here and the shape of the galaxy here, because they're both distorted by mass in between. That is very hard to do. Cosmic shear is hard work. The shear can be as low as 0.1%. Okay, that's a deviation, so something with an axis ratio of 0.999. And we have to be able to calibrate that itself to 1% to get a reasonable result. So it's really tricky, not on a galaxy-by-galaxy basis, but systematically over the whole survey. Major surveys take many years, as this diagram shows. So the left hand of each bar is when the observations for that sample were complete, and the right-hand bar is when they published their first cosmic shear paper, right? And it's typically 4 to 6 years. In fact, DES year 6 is not, we don't know when it's going to come out, probably soon. So it's hard work to do this image simulations, to calibrate, and do all this that you need to be confident about your results. These surveys started in 2011, 2013. As you know, UNIONS started in 2017, and it's taken 9 years, which is very long compared to our competition. So we are a little bit behind. Had we been able to accumulate data faster, had we been given, for example, a community survey, this might have all been advanced by 3 or 4 years. But it is what it is. So I will skip this and just put up my conclusions.
Thank you, Mike. Questions, please.
Thank you for this nice talk. On the filament measurements, how do you select your? I mean, you're only your photosy, or you're taking research?
The question, and I'll repeat it, is for filaments, how do you select them? And in principle, you think you could do with photosys. We tried that with a previous survey. It doesn't work. So these the halos are selected from BOSS. So they're luminous red galaxies. And that's another example of where spectroscopy plays a big role, because having the spectroscopic survey allows us to select filaments where we know the two are the same distance. And in fact, we can even make control samples where the projected separation is the same, but they're not at the same distance and hence not connected.
Very nice work and very impressive variety of topics. I think DES is shorter because they are only focused on cosmic shear, but you did a lot of range of science. Can you go back to the slide you showed the subhalo mass versus stellar mass for the tidal stripping? So you said that I think you picked all about 10 to the 11 solar mass halo.
Yeah, there are other red mapper galaxies basically that are picked out by the red mapper galaxy, but algorithm, but they tend to have stellar masses around 10 to the 11.
But I'm curious about the host halo. What is the rough, vary radius in this? Are you also picking the host halo in some way? Because I assume this is correlated with how the vary mass or vary radius of.
In this case, they're all red mapper clusters. I don't think, if I remember, there was any selection on richness, so there'd be the range of richnesses. And it's true that You could scale it by the virial radius. We plotted it this way because that's what other people have done. It's easier to compare.
Bring them in different groups with different virial mass.
We haven't tried that. It's a great idea. The problem is the error bars are a little bit big, so when you split things in two, they all puff up. But it's on the list.
Great. On that note, let's thank Mike again.